Hi everyone, my name is Vikram Ramaswamy and I would like to talk about our paper Overlooked Factors in Concept-Based Explanations, Dataset Choice, Concept Learnability, and Human Capability. This is joint work with Sunny Kim, Ruth Fong, and Olga Rysakowski. Deep neural networks are increasingly being used in high-risk settings. In order to responsibly use and deploy these networks, we need these models to be interpretable. Concept-based explanations focus on explaining all or parts of the model using human-understandable semantic concepts. An example is shown here, where we have an explanation for the model scores for the class bedroom based on the presence or absence of certain objects, like bed and coffee table. While these methods are excellent for bridging the gap between humans and models, we find that current concept-based explanations make several implicit decisions when constructing the explanation, all of which affect the final output. We investigate three different factors of current concept-based explanations. First, we show that the explanation output is heavily dependent on the dataset used to train the explanation. Next, we see that the concepts used can be hard to learn. And finally, we show that these explanations can be overwhelming to people due to the complexity of the explanation. Through the rest of the presentation, we will go through these results in more detail. Before that, let's illustrate how these explanations are trained. Concept-based explanations explain part of the model or the model output using semantic concepts. Typically, these are trained using the black box model and a dataset labeled with the concepts, called the probe dataset. These explanations learn to correlate the model's output with the presence or absence of the concepts labeled within the probe dataset. We note that the probe dataset may not be the same dataset as the training one. For example, scene classification models trained on Places 365 are often explained using the Bruin dataset, labeled with objects and parts. Shown here are two examples of concept-based explanations. On the left, we have NetDissect. This is an explanation that labels different neurons with concepts. On the right, we have IBD. This expresses the model's output in terms of a linear combination of different concepts. Given that these explanations are trained using the probe dataset, we can ask if changing this dataset affects the explanation. For a fixed scene classification model, we construct explanations using different probe datasets, ED20K and Pascal. We find that the explanation output can be very different based on the probe dataset used. On the right, we have a table of tables of different neurons using NetDissect. In the top rows, we see that some neurons are labeled with similar concepts. For example, neuron 9 is labeled as plant when using ADE20K and potted plant when using Pascal. On the bottom, however, we see that neurons are labeled very differently. For example, neuron number 185 is labeled as chair when using ADE20K and horse when using Pascal. Out of all the neurons that are labeled by both datasets, 56% of them correspond to different concepts. We find similar results for other explanation methods as well, showing that the probe dataset used can have a massive impact on the explanation generated. Next, we consider how learnable the different concepts within an explanation are. An implicit assumption made in concept-based methods is that the concepts used are easier to learn than the target classes being explained. For example, if the class bedroom is being explained using the concept bed, among others, we would like the model to first learn the concept bed and then use this in order to predict the class bedroom. However, if the concept bed is harder to learn than the class bedroom, this would not be the case. Thus, we compare the learnability of concepts to the learnability of the target classes. We find that the median normalized AP of models that predict the concept is much lower than the median normalized AP of the target classes. Shown here are explanations using IBD for 7 random classes from the Places 365 model. For each class, we see that at least one concept is harder to learn than the class itself. For example, in the third row, we see that toilet is harder to learn than bathroom. This also holds true for explanation methods that use different probe datasets. This shows that concepts used within an explanation can be harder to learn than the target classes. Finally, we consider the complexity of these explanations and how well humans can parse these. Current concept-based explanations use as many concepts as are labeled, which can be very hard for humans to understand. We conduct an IRB-approved human study to understand if humans can predict the model's output based on the explanations. We show participants an image and a set of concepts and ask them to identify whether each concept is present or absent within an image. We also show them explanations for 4 different classes and ask participants to select the class that they think the model will output. We ask the participants to reason between the trade-offs between simplicity and correctness when weighting the number of concepts. We find as the number of concepts increase, participants struggle to identify the correct class, and most participants prefer explanations with fewer than 32 concepts. We have shown that concept-based explanations currently can be heavily dependent on the probe dataset, use concepts that are hard to learn, and be more complex than people can understand. Thus, a good question to ask is how we can modify these explanations to be more useful to humans. Our work yields immediate suggestions. We can choose the probe dataset to have a similar distribution to the training dataset. We can use easily learnable concepts, and we can limit the number of concepts used within explanations. In the future, however, we need to collect more diverse and high-quality probe datasets. We should also consider developing more causal explanations, which can go beyond exploiting correlations between the model predictions and the concept occurrences. If you're interested, you can refer to our paper for more information. Thank you.